Okay, so there's a graph of velocity time here for our AP Physics C students. And our goal today is learning something about integration. So we analyze our graph. We see that there is a downward slope here, constant. So there's a constant negative acceleration happening. What we want to find is the displacement this object is going through from time equals 0 seconds to time equals 10 seconds. Let's first of all interpret our equation. The line of best fit is y equals negative 3.3x plus 22. That really means velocity equals minus 3.3t plus 22. Okay, now let's analyze that a little farther. Velocity is the slope of the displacement time graph. So what really is velocity? Well, it's dx dt. X standing for displacement and t for time. So dx dt equals a negative 3.3t plus 22. Let's apply the separation of variable technique. Let's move dt to the other side. So really we have dx is equal to negative 3.3t plus 22 and a parenthesis around that. And then we'll sneak in a dt outside of that. So in order to get displacement from a velocity time graph, we need to take the integral, which is really the antiderivative. So we're going to do that algebraically, and then we'll go back and look at that through the graph. So let's go ahead and write this. So I'm going to take the integral of dx, and that'll be equal to the integral of negative 3.3t plus 22, and then a dx outside. Okay, so we need to think antiderivative, the backwards of a derivative. So the antiderivative of dx would just be x. And that's going to equal the antiderivative of this right side here. So a negative 3.3, we're going to take t next to that back up to the squared. And to get that negative 3.3, what would we have done? Well, we would have multiplied a number in front of that by 2. So now we're going to do backwards. We're going to go minus 3.3 divided by 2. Okay, so then when we take the derivative, 2 times this expression here leaves us with a negative 3.3. So you got to think backwards here. Now let's go plus 22. And we're going to put t in front of that. Okay, now t to the first power. Okay, so again, think backwards. A t would have been there in the original equation. And then plus c to end it. C is the constant of integration. We just don't know what it was before the equation was actually, before the derivative was actually taken care of to get this equation. So we just put a plus c there. We don't know what it was. Okay, now this is called an indefinite integral. What we really have is a definite integral going from time equals 0 to time equals 10. So I'm just going to work with the right side of this equation. We want a definite integral, and this is how I write that. So a negative 3.3 divided by 2, okay, is negative 1.65. And that's going to be a t squared plus a 22t plus c. So what I'd like to do is put a bracket around that. And I'm going to put my limits of integration on the right side of this. We're going from time equals 0 to time equal 10. So now what I'll do is I'll put 10 seconds in for this equation, and then I'll put 0 seconds in, and I'll subtract those two to get my definite integral. So let's go ahead and do that. So that's negative 1.65 times 10 squared plus 22 times 10 plus the c, which we again don't know what it is. And now we're going to subtract from that 0 plugged into all of this. So a negative 1.65 times 0 squared plus a 22 times 0, and then a plus c. Okay, now what you're going to notice is this whole expression here, that's all 0. And then our plus c and a minus c, that actually cancels out. So we're really only evaluating this part right here. And we're left with our answer is going to be 55 for that. So that's 55 meters. Okay, and that's how that's done. So, but what about the actual graphical way of doing it? Well, taking the integral is the same thing as taking the area under the curve of the graph. So what do I have here? Well, I've got area here And again, it's going to be bound by the curve to the x-axis. So I'm just going to kind of highlight this area here or shade it in a little bit. And we see that we have from 0 to about, maybe about 6.7 here. We're going to have to estimate that a little bit. And then we've got an area from here to this, the 10 mark. And I'll just kind of like put a little line there. So we got this triangle here and this triangle here. Now this triangle is below the x-axis, so it is negative. So we've got to treat that as negative. So we're going to add the area of this plus the area of this. And that will equal what you got by the algebraic way of doing it. So area of a triangle is 1/2 base times height. So let's do this one here. So that's going to be 1/2 the base, which is 6.7 about. Now again, this will be an estimation, of course. And then about 22 is the height. Okay, so 1/2 the base of 6.7 times the height of 22. Okay, now what about the next one here? Now this is going to be a minus 1/2. Well, I know the rest of the way is 3.3 to the 10. So 3.3. And then our height is about 12. So I'll make that 12. So I'm going to take the area of this triangle here and add it to this triangle here. But remember, this is a negative area. And the answer comes out to be 54 meters, which is a pretty good agreement, okay, to our algebraic way of doing it. Now, of course, we believe the algebraic way is more precise in this case because we are not guesstimating from a graph. So that is an integral. And again, just a quick reminder that when you don't actually evaluate from one part to another part, it's called an indefinite integral. But when you actually evaluate with what are called limits of integration, that is a definite integral.